Okay guys, let me apologize there because I just realized that I went through a whole page of notes and I didn't record it. So what you're seeing is the work, and so let me go ahead and kind of battle through that and kind of talk to you what I did do. So first of all, what we're trying to do is you're given a picture and we're going to try to find the function that fits the picture. So it's the reverse of what we have been doing. I gave you the equation and then we graph the picture. But now I have data. What's the quadratic that fits it? We can see that both of them are parabolas, so we are talking about a function, and right now we're in standard position. And so the first thing we need to do is find h and k. So on this first graph, right, the typical function goes through 0, 0, and it looks like it's been shifted to the left 2 and up 1. And we can physically see that the vertex is at negative 2, 1. So that tells me h is negative 2 and k is 1. So we're already there. So that's what I did here, right? I'm replacing that h with negative 2. I'm replacing that k with 1. When I subtract a negative, that's a positive. And this mimics what we have, right? X plus 2 means we're shifting to the left 2. And plus 1 means we're shifting up. So all I have to do now is find that value of a, right? So how do we do that? We go use a data point. And what I chose to use is the 0, 2 right here. And when I plug that 0, 2 in, right, f of 0, for what I have, we replace the x with 0, and it would be equal to 2. 2 squared gives us 4, right? So 4a plus 1 equals 2. If I subtract 1 from both sides, I get 4a, right, equals 1. And if I divide both sides by 4, I find that a is equal to 1/4. So this picture, right, is basically our original function being squashed down a little bit, being vertically compressed. So the function that fits this is 1/4 x plus 2 squared and then plus 1. So there you have that. So hopefully, again, I meant to battle through and do the work as I talked, but hopefully seeing the work and then having me flesh it out does the same thing. So doing the next problem, the same idea. We initially recognize that it's going downwards and it's a little skinny, so I'm expecting my a to be negative and the absolute value of a to be greater than 1. That'll cause it to stretch, and the negative will cause it to flip. Right away I see that the vertex is sitting at negative 1, 8, so I know exactly what my h and k is. H is negative 1 and k is 8. So when I go to my form, right, let me rewrite it up here. Right, when I go to my standard form, we're replacing the h with negative 1 and replacing the k with 8. Okay, cleaning that up, we're there, right? So my f of x is some a value, x plus 1 squared plus 8. So now we got to figure out, well, what's my a, right? I'm anticipating what it's going to be, but what exactly is it? And that's where we use a data point. So when I look at my graph, one easy data point is the y-intercept. So when I put 0 into the function, right, I'm replacing that x with 0, and what it's supposed to be equal to is 6, right, because 0, 6 is on the graph. And so now, right, 1 squared is 1, and we have plus 8, so a plus 8 is equal to 6. Subtract 8 from both sides, we get a is equal to negative 2, and that's exactly what we expected, right? So it's negative, meaning we're going down, and it's 2, meaning that we're getting a little skinny. So what's the function that fits this data? Negative 2, parentheses x plus 1 squared plus 8. And again, you can readily check these. If you put these both on your graphing calculator, you will see that we're a spot-on fit. This graph would top out, right, would have a maximum at negative 1, 8, and it would have a y-intercept of 0, 6, and it looks like negative 2 comma 6 is also on a data point. So you can verify that on your graphing calculator. And same thing with this one. If you plug this on your graphing calculator, you would observe that negative 2 comma 1 is the vertex. It's 0, 2 is its intercept. And if you were looking for another data point, negative 4, 2 would be another data point on the other side using that axis of symmetry. So that's another payoff behind the standard form. It's relatively easy to curve fit. Just find your vertex, you got h and k, and then use a data point to help you find your a. And you basically have the three big pieces. You have your a value, your h value, and your k value, and you're off to the races, and you've got a good curve fit. All right, so more coming later. Excuse me. Right now everything is easy because it's standard form. What happens when we have something that's not in standard form? We'll investigate that in a new video coming soon, and I promise to turn the video on when I start, not when I end. Talk to you guys later.